Hello guys, in this lesson we will try to create a Matlab Simulink model to represent the suspension with car dynamics model. In the Matlab Simulink application, firstly we need to understand how to use the Matlab IDE, Integrated Development Environment, and so we have a command window in here to write a specific code to be accomplished by the compiler. And so we have a current folder in order to store any library or the Simulink file, and workspace stores to any variable producing by the Matlabs. Okay. And so in order to open the Simulink window, you can push the Simulink button in here, or you can write the Simulink in here and push the enter button. And so we have a start page for the Simulink application. Blank model is the empty model in the Matlab Simulink application. And so if we push the left click on this button, and so we have the untitled Simulink model. Okay. And so firstly we need to save these codes like this one, where one sus car dyne which is the name of this file. And so secondly, we need to set the new model configuration parameters in here. With the parameter of the solve selection, the fixed step should be selected in here in order to get the more realistic results of this code. 0.1 milliseconds or the 1e over -4 should be selected in the fixed step size, and then we are ready to create a model. Firstly, we need to add the Matlab function blocks in here in order to emulate the specific system dynamics or the state space representation of this model. Okay, and so suspension car dynamic, which is the name of this function, and so this function can be implemented by the output and input value. Okay, FGN is the function name, and so sus car dyne, which is the name of this function. And so in order to emulate the model of the car suspension system, we need to create an output z dot, and we need to get the input value z. Okay, and so also ff should be provided by another function, because we want to try to acceleration and braking condition in this suspension car system design. And so we need to add this function block or the input arguments to our code. Okay, and so z dot can be obtained by the az plus bff, because our system dynamics model creates this dynamic. Okay, and so how can we create a proper dynamics in the Simulink application? In the Matlab Simulink application, everything is the operation of the iteration process, which means that the number or any value is created for a instantaneous time, or at each time. Okay, and so if you have an equation of motion like this one, state space representation, this is the derivative of the z transform, and so we need to obtain the z value by using these things, because this is the dynamic equation of motion of our study. Okay, and so the integrator can be added in here in order to collect, or in order to sum this z dot value and convert it to to z value. Okay, because in our application the iteration is going through the 10 seconds or this seconds. Okay, and so we need to add this notation of motion in here, and so we generate the z dot value, and so integrate it, and then we obtain the z value. Okay, at each iteration the z dot is produced and the next z value is obtained, and so this z value is used to obtain the new z dot value, and so iteration is completed. Okay, And what about this? Our equation is that the two states, okay? And so we need to have the two initial condition in here, theta car and theta car dot, okay? And so we need to implement these coefficients of motions in here, and then we need to write these codes into the Matlab function, okay? And so in the Matlab function block, we already write this output value, but we need to create a specific matrices, okay? And so the A and B value should be written in this position. And so what about the A matrices? A matrices is equal to the what? Is equal to the like this one. Look at this, the equation of motion, and so 0, 1, and so in the second place kt can be obtained by using the minus kt terms divided by I car, okay? And so minus ct is a collective term, and so the I car should be written in here. And so in the B matrices 0 comes with LH divided by I car value, okay? And so we need to define the kt, ct, and other constants in our matrices, okay? And so matrix parameters can be defined by like this one. First, the kt is equal to the what? Lf times chi yf plus lb times chi yb. And so Lf and Lb is equal to each other, and KYF and KYB is equal to each other, and so this form is obtained. But in the Matlab Simulink application, the generalized form should be written, okay, in order to understand every mechanism of these things, okay? This is the summary of this code, but this is the general form or completed form of our KT matrices or the constants, okay? Ct is equal to the what? Ct is equal to the Lf times Cyf plus Lb times Cyb, okay? This is our general notation. And so I car should be provided by using 1 divided by 12 m car times what? Square these things, and so the Lb times Lf divided by 2. This is the general inertia calculation of this car model, and so this is a road calculation, is a simplified modification, but m car times Lb plus Lf, the center of gravity, is provided in here, and so you can calculate the I car model in this notation. But you want to use you can choose the different calculation of the I car or inertia of the car model. Okay, you should check the Wikipedia to eliminate the other choices, and so you can choose the different path or different formula to obtain the inertia of this car. But in this notation, I choose the simple road, the turning around the z-axis in our dynamics, and which is this formula, okay? And so what about the constant parameters? Constant parameters. And so Lb is equal to the 1 meter in here, and so Lf is equal to the 1, but we can choose the different number of the assigning to the Lf. Lh is equal to 0.5, okay? M car is equal to the 100 or 1000 kilogram, and Kyf is the suspension ratio 1e5, Kyb is equal to 1e5, and so Cyf is equal to 1e3, Cyb is equal to the 1e3, 1000. In the first place, we can choose these coefficients, but in the next stage, in our time response, obtaining the time response, we can choose different k values or c values, okay? And so we also create the theta matrices in here, theta creation because the theta is equal to the what z1 comma 1, and so theta dot is equal to the what z2 1. Okay, these are state parameters, and so we can use it in order to calculate how much force on the suspension system. Okay, these are general notation of this code, and so we can emulate this diagram by using this notation. Okay, and so if we rerun this program, and then there is no error in here, but there is no meaningful results because we don't provide the FF force into this sus curve dimension, and so we need to create this force value in order to emulate our car dynamic system. In the next lesson, we will create this FF force, and so we will test our suspension car dynamics in our system. Okay.